this is going to be a two-part lesson on one set of slides. So first we're going to talk about acid and base strengths. And we're going to start with acids. Your really strong acids are going to completely ionize or dissociate in water. So they're going to break apart. You're going to have one hydrogen break off from the rest of the ion. Strong acids are going to be good conductors of electricity because there's going to be a large number of ions in the solution because they have completely dissociated. So for example, if you have hydrochloric acid, which is HCl, this guy is going to break and you're going to be left with a hydrogen ion and chloride ion. Now these guys are not going to want to go back together, so you're going to have a lot of ions present in the solution. Here's the example again. You have hydrochloric acid, add it to water, you get hydronium, which essentially is a free hydrogen electron here, and your chloride. Your weak acids are going to slightly ionize. Okay, so there's not going to be a complete dissociation. They tend to not be good conductors of electricity. There's not as many ions in the solution. So for example, if you have acetic acid and you add it to water, this hydrogen here is going to break off and give you the acetate ion, but you also have the reverse reaction where these two are going to come back together and give you acetic acid again. So you're not going to have as many ions present in the solution, therefore it's not going to conduct electricity as well. Your bases, strong bases, again, are going to dissociate completely into a metal ion and the hydroxide ion. So for example, sodium hydroxide, here is your metal ion and the hydroxide ion. Okay, so separated completely. Weak bases, just like your weak acids, are going to partially dissociate. You get a conjugate acid and hydroxide. So in this case, we have methylamine plus water. You're going to have hydrogen come off of the water, attach itself to the amine portion here to give you hydroxide and your anion, your conjugate acid. Again, since it's a reverse, there's not going to be as many ions present in the solution, so it's not going to conduct electricity as well. Alright, so that brings us to dissociation or ionization constants. There are three we're going to focus on. One, which is the acid dissociation constant, K subscript A. And that's going to be your ratio, so we're going to be using division, of the concentration of the dissociated form of an acid to the concentration of the undissociated form. So your Ka is your Ha, or your hydrogen ion plus your anion. Okay, so this is going to be your dissociated form over your undissociated form. So it's the acid still intact. Right? Since our ions break apart, or our acids break apart one-to-one ion, your hydrogen ion is going to equal your anion concentration. So if you have hydrochloric acid, when it separates into the hydrogen ion and the chloride ion, for every one hydrogen, you have one piece of an anion. So they are one-to-one, so for our purposes, we are going to consider them equal to one another. So that constant is going to tell us whether reactants or products are going to be favored at equilibrium. So when your reaction balances itself out as far as its rate. Your weak acids are going to have a low Ka, meaning less than 1. That means you have a low ion concentration. Your product is low. So remember, our ions were in the numerator, the entire acid was in the denominator. You have a small number over a large number in a ratio. It's going to give you a value less than 1. You have a high molecule or reactant concentration. That's your denominator. So weak acids, less than 1, not a lot of ions. Strong acids are going to have a greater than 1, high Ka value. So your numerator is going to be larger than your denominator, so you're going to get something over 1. Now, high ion concentration, remember they dissociate completely. And very low molecule concentration. They're not going to go back and bond together. They have separated. They like it that way. So we have a 0.1 molar solution of acetic acid. Tells us our hydrogen concentration is determined to be 1.34 times 10 to the negative third molar. They want to know what is the Ka of the acetic acid. So here we have 0.1 molar. This is going to be our acid concentration. Okay, which is going to be acetic acid, so you can write it HC2H3O2 if you'd like. That's going to equal 0.1 molar. And then here is our hydrogen concentration. Okay, and because it is the hydrogen concentration, that is also going to equal our anion concentration, which in this case is the acetate ion, C2H3O2 negative. Remember, they are equal to each other. So hydrogen and acetate both going to equal 1.34 times 10 to the negative third molar. So Ka is going to equal our anion and hydrogen concentration. Now, because they are one and the same, for our purposes, we can simply square them. So 1.34 times 10 to the negative third squared divided by our acid concentration, which is 0.1 molar. Molar up here, sorry about that. This is actually going to be unit less. So your Ka is going to be 1.34. Make sure you're using your EXP key here. To the negative third. That is raised to the second power squared divided by 0.1. And our answer should have 1 sig fig. Put the 1 up here. And we get 2 times 10 to the negative fifth for a Ka.